So now we'll essentially use everything which you have done in the last few classes. Most of it is just reusing in the clever. Okay, so I promised there will be more complicated graph. So percolation. Is it not screen? It is stuck now. Percolation. SINR. What are you doing? Does it? Okay, so just to remember the locations of columns is going to be opposite point process within density that is called node locations. And let's look at two special nodes, X and Y. So the distance between them, d of x. So the signal power between x and y is some function of d of xy. G can be any decreasing function. In particular, most often used is g to the minus alpha, where alpha is greater than equal. We'll write everything in terms of g. You can make it particular special case where it is power loss. Interference power at y is summation of g of d z to y. So z down other than x. So all of them are transmitted at the same time, so they result in interference at y. And noise power is something in zero without loss of the matter, we can take it. It won't change it. Okay. So then an edge exists between x and y. So an edge exists between x and y. If the noise power, which is the signal power, is given d x y divided by the noise power plus the interference power g of mu power. Greater, so the noise power, some underlying is greater than the threshold. This is clearly directed. That much is clearly clear that this is producing a directed graph. If an edge exists between this and this, does not mean that the reverse edge exists. Because the interference received, see the signal power will be the same, but the interference received at this point might be very different. So this is producing a directed graph. That's the first thing we're departing from our usual Gilbert's response. Any questions on the graph? So this is completely defining the graph. Node locations are.
Can you please define it?
Sorry?
The interference power.
Yeah, what is the look at all these which are other than x. So every single point in phi. I'm adding all the energy which is coming from every other point other than x. Okay. Do not get?
we are defining interference point at x with respect to some
At y.
at y
Yeah.
with respect to some particular point x.
So, with respect to XY communication,
Okay.
what is the interference received at Y will discount the power received from X, which is the signal power.
Okay.
So everything else I'm counting in the interference.
For 2 points in the bulk of the graph, how would the interference
Say this again.
for 2 points inside the bulk of the graph,
What is bulk?
not at the boundary?
There is no boundary. It's a Poisson point process. It's defined over R2. So there is no boundary.
How would this interference be different for two vertices?
So let's look at this point.
And
This point. The same interference coming from every other point, including this.
yes,
Similarly, this is same interference coming from everywhere else, including this. For realization by realization, it's going to be different. In terms of distribution,
it won't be very much different. Right?
now this is simple random variable. Two random variables are identically distributed. Doesn't mean anything about what is the probability that they're identical. So what is this randomness? The randomness is the Poisson point process. Once you take a realization, it's giving you exact locations of these points. Now for that one exact location, the interference seen by this node and interference seen by this node is entirely different. It's correlated, but different. I'm not saying they're indifferent. I don't see the problem. Tell me what different. Directed, okay, so convince me that if an edge exists this way, this condition is automatically satisfied the reverse way. So this is the same, this is the same, this is the difference. Because the locations are different, so the interference theory is also different.
The interference will be very different from all the versions.
It's not a question of how different. Even if it is slightly, so suppose this is equality, even if it is little more, it will not be satisfied.
Okay.
There is no guarantee that both sides.
Yes.
All you're saying is correlated, which I agree. They're not equal. Okay, so what do we want to understand? We want to understand. So think of usual conditioning that there is a node at the origin, which we did, and everything else goes through like this. What is the connected component size of that node at the origin? And what is the probability? We do a definition of percolation. Is the probability connected node at origin is unbounded. Is that's what we're interested in. So what we do is we'll insert a parameter. So what did I say that SINR was the signal which is G of dx your knowledge power plus the summation of G of dz y z b without. So insert a parameter gamma, we should suppress the interface. So gamma is greater than. Right. Suppress. So this is a technology driven thing, but in terms of the math of it, all I want to understand is if there exists a gamma, which is small enough, such that I can make this probability greater than 0. See, as this goes to 0, the percolation probability increases. The gamma goes to 0, what happens? What does the graph look like? Take it equal to 0. Suppose gamma is 0. What does the graph look like? And the connection on the graph is whenever SINR is. Tell me, as gamma goes to 0, what does the graph look like? It looks something similar to what we studied already. Right, just with appropriate. So as long as so take n0 equal to 1. Greater than equal to what is implied is that v of x1 equal than the inverse of the. So this is nothing but the new radio range which we understood that any two vertices are connected as long as they're within a distance of radius r from. So if gamma goes to 0, this graph just looks like a Gilbert test model. So what I want to understand is that is there a value of gamma small enough for which I can claim that there is percolation here as well. That's what the really important question we were trying to answer. Because it's not necessary that for all values of gamma there will be percolation. That is something which is possibly not even true. So you can call it the interference suppression parameter for the moment. Okay, so now given that we are naturally here, what is the subcritical regime for this graph? Subcritical meaning when is there no percolation? Can you just use the observation on the board right now to tell me something about when is there no percolation? Right?
Gamma is good.
Gamma is 0. That's what I said, whatever naturally we are right here. So the easiest thing to think of is gamma, just make gamma equal to 0. Then what can you say? When is there no percolation? You just said something like this graph is equivalent to some other graph. Okay, so when is there no percolation? Then Gilbert disk model. You don't have to look back at it. You can tell me abstractly. I'm not expecting any numerical answers. All I'm expecting is conceptually you understand what it is. So if gamma is 0, this graph is equivalent to a particular Gilbert's disk model graph.
Are equal to G inverse of beta.
Right.
And if G inverse of beta is too small, then we can use the threshold of the Gilbert's disk model as.
Correct. So let's compare the G equal to beta with respect to the critical value of R. See, lambda is fixed for both models.
Yes.
And there is a particular critical value which you have not identified, but there is some critical value. So as long as G inverse of beta is less than that critical value, there can be no percolation. So at least we know something about this particular graph, but just by mapping it to gamma equal to 0. And we know that a higher gamma is only going to result in worse percolation properties. That also you should be able to convince yourself.
Yes.
So no matter what gamma you pick, as long as G inverse of beta is smaller than the critical value for the inverse disk model, there can be no percolation. So that's the first observation we make in terms of the subcritical regime. You can make it more complicated or you can define it better, but for the subcritical regime, we're going to leave it there. Now, question is, when does it percolate? Here we are saying if G inverse of beta is smaller than the critical value for the inverse disk model, there can be no percolation for any value of gamma. Because gamma equal to 0 itself fails. So now the question is, does there exist a value of gamma for which there will be percolation in this graph? So again, use whatever we've done so far. There's nothing new to be really done. All we have is the Gilbert system. That's all we do. So what all can you observe from this? Is there any percolation for all values of gamma?
As soon as we introduce gamma, the mapping is lost, right?
No, the mapping remains, right? So gamma equal to 0 mapping is there. So any higher gamma is only a subgraph. So for gamma equal to 0, you get a graph which is identical to the disk model graph.
Yes.
And as soon as I increase the gamma, the only thing which can happen is I can drop certain edges. Nothing else can happen.
Yes.
So it's definitely a subgraph. I can't create new edges because this is a quantity which is always greater than 0. That's why the noise power is there. Otherwise, some crazy things can happen. Supposing your Gilbert disk model is percolating. No, think about it. So in one side, what have you said? That if the Gilbert disk model itself is not percolating, there is no chance this can percolate. That's what we really said. Now play it around. Suppose the Gilbert disk model is percolating. Now what can you say? Now what is the obvious expectation?
Now it will depend on gamma.
Yes. So what do you expect to happen? Will you get percolation for all values of gamma, or
In the experiment, we won't get percolation, and then as we reduce gamma, we get a threshold where percolation will happen.
yeah, but how do you know that it is not 0? That threshold. That's the difficult exercise. Because at 0, I know it's the same graph as before. So if that is percolating, is also. All the non-triviality is that can you show that for small enough gamma, which is not 0, this graph percolates as long as my Gilbert's disk model percolates. That's all we are going to show. But before that, I just want to understand this graph. That is it, all of this claim that as gamma goes to 0, this graph more and more looks like the Gilbert's disk model. The non-triviality is that the threshold at which you expect it to start percolating is not 0. The value could be small, but strictly not there. Okay, so suppose I want to do this adventurous exercise. How do I proceed? So essentially, what I'm going to assume that the Gilbert's disk model for an appropriate R is percolating. Now what do I do?
Reduce small gamma.
That will be complicated. Directly saying that, how do you pick the small? How small? That's the crux of it. It's an interesting concept. So the first piece in the construction is that so lambda is fixed, right? Lambda is fixed. R is such that the Gilbert's disk model. Essentially, what we're saying is R is greater than critical radius. Okay, so this one. And now look at this Z2 lattice. So intentionally make it very large. This is my square lattice. This usual Z2, I'm just making it large for a particular. I'm going to define the square lattice edges to be open and closed depending on what is happening in my Gilbert's disk one. So this side, so side of the disk is correct. This is some S. This is also S by. So I'm going to look at this by 2. This width is this. And gone halfway here. Similarly, one. So this is. This rectangle is on. Look at it. So this is the edge under consideration. For this edge, I'm thinking of this rectangle. What is the size of the rectangle? This is S. 3 by 2. So this is 1. This one. Much over 1. This total is S by 2. So I'm defining something in this weird rectangle. So there are two squares really, they're not looking like squares, right?
Is that 3s by 2 or minus?
So this picture is slightly missing. So this is S. Okay. This is in fact 3s by 2. Make 3 parts of it. This is by 2, this is by 2, this is by 2.
So like that part is S by 2 or the height is S by
Height is by 2.
Okay.
Height is by 2. This is also S by 2. This much.
Okay.
So let me erase some parts. So for edge E, its center is defined as XE, y. This length is S. So three squares is what I want. Yeah. This is this is the edge. This is the edge which will get mapped to the square lattice. That's why drawing that on top of that multiplier. Okay, the 3 squares. Now, what do I want to happen? I want something to happen from the Gilbert disk model. Think about what would I want to do? I want somehow that if the Gilbert disk model is percolating, the square lattice should percolate. That's what I said. And if the square lattice percolates, the square lattice percolates, then I'm going to map it to the SINR graph. In 2 steps, we're going to do this. If the Gilbert disk model percolates, I want this square lattice to percolate. And if the square lattice will percolate, my SINR graph is going to. That's 2 steps. What do I want in the following? That there should be two events should happen. First event is event A, event E is the edge with respect to A. When do I call it? AE happens if two things have to happen. That from the Gilbert disk model, there is possibly it will look something like this. The left to right crossing of the Gilbert disk model. A connected left to right cross. But this whole thing should be crossed by something like this, not connected. We'll call it one. A left to right crossing of rectangle RE by inverse. So this rectangle is called R. Is it clear what it means? From left to right, I should have a connected path. Cutting thing. Two, there should be two vertical crossings of this square and this square of the same inverse square.
What is what?
This is horizontal crossing.
Okay,
So this vertical. So something like there could be some common circles. This one. Top to bottom. Crossing of X. For the left and squares. Oh, can you think of why I'm doing anything on this nonsense? If you look at one edge in isolation, it doesn't tell you anything. If you put two edges in together, what does this mean? One left, right, two vertical. So if two edges are open, I'm eventually going to define what an open edge is. For the moment, imagine that event A, as long as that happens, I define this edge to be open. So supposing two edges are open, one like this and one like that. What does it mean? Edge being open means there has to be this top to bottom as well as a left to right cross. Similarly, for a vertical edge, you put everything 90 degrees. So this will overlap with this square of this edge. This will be the rectangle will look like this. Three parts. Now that horizontal will become vertical. This will be horizontal. So if this is open and this is open, what is going on?
So it is this and with a connected.
Exactly. So these guys will, because it's crossing vertically, it has to hit somewhere, and there is a common rectangle. So this connected component will have something to do with this connected component. It will actually be connected. That's what really this is. Okay. I have another event to handle the SINR part. So this essentially is the geometry of it is being controlled by the event A. The SINR part will be controlled by the event B. What I really want to say is that inside any point within this rectangle, the interference received is smaller than a particular value. That's what I'm going to define event B. Before that, let me define a transformation of my G function. 0 x ns by G.
This vertical crossing can happen in any of the three.
No, both. One here and one here. Could be more than one, but at least one here and at least one.
And it should also touch the edge, right?
Which one? No. I don't care about the edge. It's crossing this, that's all I care. This rectangle, this square defined is being cut by a vertical path. That's all. See, physically, this edge means nothing for the Gilbert's disk model. What I'm doing, I'm looking at this Gilbert's disk model, looking at a particular set, bounded region, and say, is there a vertical crossing in it or not? No. You should forget that edge even exists. For an edge, I'm just saying this, think of this square. Okay. And that square is being cut by the Gilbert's disk model. This is just a transformation of my usual. S is not inside this. So just redefine my G prime for a particular region. You see why, what am I doing? G was my original function. I'm defining a G prime, which is 0 for close enough points. And it's just a translation of my actual function for far enough points. So the event B will be defined to be, just look at the definition. If the interference is received at the center, which is xc comma y, at the center of edge under the function g prime. This replaces the interference was summation of g over this, replace that g by g tilde. This was the interference, the original interference. And they say under g tilde, so it is replace g with g tilde. I'll connect it to the actual interference. The window receive the center of this under g tilde is less than equal to some quantity. We choose them later. So BE is 1 if this happens. KE is 1 if this happens. Otherwise, they're 0. So binary events. What I'm saying, interference seen at exactly this point is at most time under the function g tilde. What does it mean? Why am I defining this? What is the maximum distance from this point to this? That is precisely what that number is. Square root 10 square. So if the interference seen here under g tilde is less than m, this tells you that the interference seen at any point, in particular the corner points, under g is at most. That's what is going. Do I want to do write that again? Or? Under g tilde, interference seen here is at most 10. At most 10. M. Some quantity which will pick later. This implies that interference seen at any point inside this rectangle under the function, original function g, is at most. That's how it has been defined. So if you want to take it the reverse way, the g tilde has been defined in such a way that this is one particular example. I'm just translating it.
Why is translating?
Why? Because I want to control at one point while implying that at every point this is at most. I don't want to control at every single point. I could have defined BE to be the event that at every single point inside this rectangle, the interference received is at most time. So there are too many points to answer. So I'm defining at one particular point and translating it using the change definition of g tilde to every other point automatically. Okay, so now we see what is going on. So an edge is defined to be open finally. So edge P is open if both A is equal to 1 and B. Alright, that's my final definition of an edge being open in square lattice with side edges. So absorb it and then think about what will I do. So M for the moment is a variable. Some upper bound.
For the points inside this rectangle, there are no difference.
No, we're not saying anything. At that point xe comma y, the interference is at most M. That's it. When the function evaluation is with respect to G tilde. This is my definition. There is no problem with the definition. Is it useful or not? That's a different story. It could be that B is never 1. Right? In which case, whatever I am doing is useless. But I'm defining for the moment that divide B is equal to 1 as long as this happens to be true. What is essentially implies is that any point inside also has upper bound on the interference with respect to G, not with G tilde. So now what can you say? Supposing now my square lattice in this definition percolates. What could you say about the SINR? Does that percolate? See, we already taken the Gilbert's disk model to be percolated. Now, suppose you are given that the square lattice also percolates. What can you say about the SINR graph percolation?
We need to replace G by D tilde now for the activity.
No. The definition of the original graph will remain with respect to G. I just defined is in between M and T, B. I'm not changing the definition of the graph. The graph is two edges, two nodes are connected in the SINR graph only if the SINR with respect to function G is greater than equal to beta. That is not being changed.
Now you're seeing the total interference in the
That's it. So now think of supposing the
then it can percolate if the final.
no. Now come to the question of can or cannot. Does it or not? So if the square lattice is percolating, is my SINR graph also percolating?
Yes, and now the radius would depend upon this upper bound and
Yeah, that's correct. So now tell me everything. So first of all, why should I do it? You have to give me some picture argument first. that if the square lattice is percolating, so does my SINR graph. I've drawn these lots of circles, right? Circle essentially mean that there is essentially an edge between them.
Yes.
So if there is an edge between two nodes of the Gilbert disk model, and if the edge is open, what is it imply in terms of the
So this model is essentially percolating.
disk model is percolating in edge is open, so that means this vertical path and horizontal path exists, as well as this condition is also true. Now, two nodes which were connected in the Gilbert disk model, are they also connected in the SINR model is the question. If you can convince me that, that is sufficient. Because we know that Gilbert disk model is percolating, and there's such paths which are crossing, so it will eventually the SINR graph also will be percolating. So what is the distance between two connected nodes in the Gilbert disk model? Nothing to think on that. We started with the percolating Gilbert disk model. So what is R? R is anything smaller than the critical radius. I don't care how small. So what is the signal power between any two nodes connected in the Gilbert disk model? Greater than or equal to G of R critical. Why everything is so if the Gilbert disk model, two nodes are connected. When are they connected?
R is greater than RC.
The distance should be less than RC, right? This one they're connected. So what is the signal power between them? If D is less than RC, what is the signal power? G of X greater than or equal to G of RC. Now, these X and Y belong somewhere here. This is an X and this is a Y. This condition is giving me some top product. What is this condition giving me in terms of interference seen at Y? Interference seen at any point inside this rectangle is how much? Less than equal to F. So it's SINR between X to Y is greater than or equal to G of RC or F naught plus gamma times F. Okay. Now what should I say? I know that RC is some specific number because that's my critical percolation, critical radius for the Gilbert disk model percolation. And all I want is this to be greater than beta. What do I want? That any two nodes which are connected in the Gilbert disk model should also be connected in the SINR model. So I can pick a gamma. Is that this condition always true? So pick gamma such that G of RC for any fixed time, whatever the time I might choose, however large M can be, I can still pick a gamma such that this is true. You are able to ensure that G of RC over N naught is greater than beta. That is given to you. So this is going to be my choice of gamma for which this is going to work. So at least what I know is that any two nodes connected here in the Gilbert Gist model are also connected in the SINR graph. Now question is, if the Gilbert Gist model is percolating, what does it mean? That this keeps going on. And I'm saying that the square lattice also percolates. Now can you say that the SINR graph percolates? All what I've shown right now is that if an edge exists between this and a Gilbert Gist model, then it also exists in the SINR model. Now you have to finish the argument saying that if the edges or the square lattice is percolating, the SINR graph is also percolating. And for that is exactly the reason that we have defined these two events. Now give me an argument that whenever AE is 1, I can actually make that work. See, whatever I done on the next board only used B equal to 1. I didn't use A equal to 1. As long as the interference was less than M, I can make that argument. But for individual edges, now if edges are percolating, why does the SINR graph percolate is the question.
So since the Gilbert's Gist model is percolating,
Yes.
and we pick the gammas is that SINR, the edge in the this model also exists in the SINR model.
Yeah.
So we do not need this square lattice.
How would you get away? Give me an argument to get away. I'll be more than happy.
We assume that this model is also.
No, that is fine. That is given to you. But that does not imply that the SINR graph percolates. Because even to define this condition, I have taken this rectangle and a square. How would you define this condition BE itself? How would you define BE? That itself needed a square lattice. So if you want to avoid the square lattice, you have to define whatever you want. Then you will have to define that at every possible point.
Square lattice is used to
define B itself.
to bound the interference.
Just look at it even more basic, right? I mean, defining B with respect to an edge. An edge is with respect to the square lattice. All of it is intimate, nothing is unnecessary. How do I define, if suppose I am not defining the square lattice, how would I define such a condition that interference is less than M? Where should I define that interference is less than M? I can't define it infinitely many points. So that takes care of that. If within this rectangle there is a connection in the Gilbert Gist model, there is also connection in the SINR. That much is given to you. But now, if I give you more, that the square lattice itself percolates, why does the SINR graph percolate? Is the question clear? Why have I defined A in the question? Simple as that. What is the utility of defining A? Otherwise, I could have just worked with B.
If the square lattice is percolating, then
Yes.
the number of vertices, so number of edges are unknown.
The connected component is unknown.
And proportionally, the number of vertices in the SINR graph will also be unknown because.
But disconnected possibly. See, you're missing a critical link. Why have I defined AE? That's all I'm asking. I could have defined AE to be nothing. I would have said nothing on AE. I would have just defined BE. Are you saying the definition of AE is useless? We have so far not used the definition of AE. Is that correct? On the next board, all we used was BE.
For square lattice to percolate, AE has to do.
No. Because on the next board, I've not used the fact that square lattice is percolated. All I've used is that if there is a link between 2 points in the Gilbert Gist model, that link also exists in the SINR. That's all I've said. So what is the utility of this event A is the question. I mean, you already saw that picture below. That picture below is the interesting. So what does it mean for the square lattice to percolate? That edge after edge after edge is connected. Now, what does that mean in terms of AE? Why am I missing that?
There should be sufficient number of edges such that the squarelet is covering them.
I don't understand this. Numbers don't matter in percolation. So suppose there is no vertical crossing. Let me define the event AE to only have a horizontal crossing. What changes? In any of the arguments you want to make. It is the square leg. These are the overlapping rectangles. These are the edges. E1, E2, this R1, R2. What do we know when the square lattice percolates that these edges, the connected component of these edges is flat. I want to imply something in terms of the SINR. So suppose you had no vertical crossings here. It's possible. In the Gilbert disk model, there's no reason to always have vertical crossing of this square. The Gilbert disk model can percolate by having a connected component which goes like this. Completely fine. But I also insisted on this as well as this, and for this particular thing, something like this, something like this, and something like this. Why? Now we should be clear. So if there is a horizontal crossing on this one and a vertical crossing on this one, what does it mean? Just geometry. Am I insisting? Horizontal on these, sorry, vertical on these and horizontal on this. If I tilt it by 90 degrees, that's what I'm doing there. What does it mean? A horizontal here, a horizontal here, and a vertical here.
So all the vertices inside these squares belong to one component.
Not all the vertices. There is a path. That's all I can. Whatever this path is, the horizontal path has to cut a vertical path here. There is no way of avoiding it. That is all we are insisting. So this horizontal path, which is crossing this vertical, so this vertical path and this horizontal path. So essentially, what is implied is that if the connected component of square that is our component, there is an unbounded connected component of the inverse this model, this manufacturing this term intersecting the square lattice. Initially, all we assume is that the Gilbert disk model percolate. That does not mean that it has to have any connection with this the way the square lattice is percolating. But by defining this event A, we are saying that the connected component is of this type. So if the square lattice percolates, definitely the overlapping, you can call it overlapping or intersecting. Gilbert's disk model also has an unbounded connected component. There could be a more which is all coalesced somewhere, but this also exists. And in addition, we have shown in the previous board that any two nodes which are connected in the Gilbert's disk model, just by the condition BE, are also connected in the SINR graph. So the end result is that if square lattice percolates, so does we follow this. This is the reason for defining these events AE and BE. What did AE do? Summarize in all words so that I don't jump.
You made sure that if two edges are connected, then the vertices inside them are also connected.
More than that, there is a path which is going along them. Because the Gilbert disk model is percolating all the information I have. That could have a connected component which has no overlap with these rectangles. Right. There's no guarantee that they have any overlap with the rectangles, which are essentially controlled by the edge being open. So if the square lattice is percolating in a particular way, what all this means is, because of my definition, that the Gilbert disk model also has a connected component which is going along the same way. And in the previous board, I have shown that any two nodes which are connected in the Gilbert disk model under event BE are also connected in the SINR graph. So if you put these two things together, what you get is that as long as the square lattice percolates, SINR graph also percolates. Now all I have to understand is when does square lattice percolate, which is controlled by the two events AE and BE. Right? So I have to somehow prove that the probability of AE BE is greater than some critical threshold. Is it clear what I am doing and what I need to show?
I do not understand the role of BE.
BE was, suppose BE was not there, then how do you claim that those two?
BE is only going to bound the
No, so how do I do this? If B is not defined, these two nodes are connected in the Gilbert disk model. It doesn't mean anything about whether they are connected in the SINR graph. The fact that
BE is different
on the square lattice, yes. So this edge is open as long as B is 1. What does it mean? That at the center here, the interference is less than M under the function G tilde, which implies that interference anywhere in this is at most M. So if there are 2 points, I draw X and Y, which are connected in the Gilbert disk model, what is the distance between them? D of XY is at most R. So the signal power is going to be at least G of R. Why is the interference is at most M? Because of my B being equal to. And that allows me to consider. So if any edge is open, it automatically means that the connected component of the Gilbert disk model is exactly equal to, it can't be larger, that will. So it better be at most the same. So under this condition, it is at most the same. So now I have to essentially look at when is an edge open, and under this condition, when is the square lattice percolated. So from this point onward, we don't have to worry about the SINR graph at all. All I have done is essentially just controlling the events A and B. Now, which of the two events is easy? Is controlling A easy or B easy? So A has nothing to do with interference. All it is saying is you define an edge, when does such a left, right, as well as two vertical crossings happen. That is directly going to come from the Gilbert disk model. B has something more complicated, where we have to worry about all sorts of properties of Poisson point process. So this is going to look at the interference seen at a particular point. So how should I control this? See, what do I have under control? The length of this edge, the width of this edge, which is S. So as S increases, what happens to this event? See, S is an artificial object. It is not given in the model. I am making a tiling of this R2 with a square lattice of size S. I can choose whatever S I want. Now, if S is large, what happens to it? Less probable or more probable. Price increases means these boxes are increasing. And remember that this is given that this is percolated.
Okay.
So what is more likely? As we increase S, are you more likely to encounter a connected component?
More like.
So this needs to be shown. But at least at intuition level, as S increases, the probability of A should increase. What happens to this? This is independent of really that. All it cares is M. So as long as I increase M, this probability I can control. So I have two parameters to play with, which are completely under my control. All that is going to do is, once I pick an M, I'll have to choose a gamma appropriately small. That's all. So I'll pick a finite M, possibly very large, for which I'll show the square lattice percolates. Given that, I'll pick a gamma such that this happens. S is completely under my control. So S and M will be related to each other. I'll pick a large enough S, a large enough M. Given that, I'll pick a gamma, which is small enough. Okay, so which event should we handle first? And what is our strategy to show square lattice percolation? That the two sides. One was if P is less than something, there is no percolation, and if P is larger than something, there was percolation. What did we do? We showed something, a particular way of showing. We looked at a dual lattice and said the probability of finding a closed circuit, if that is going to 0, then it means that the connected component. So that's what we essentially do. We look at this translation of it by S by 2, S by 2. And then think of the closed circuit. So most of the concepts are not new, they just being applied in a very non-trivial way. S prime, the square lattice plus little S by 2. So consider, and remember, when this dual lattice, if this is your original edge E, the dual edge was E prime, the vertical, and this is open, only that is open, vice versa. So consider n distinct edges. Doesn't matter if the dual or not. What is the problem? K1 is 0. K2 is 0. Yeah. So, remember, AE is defined, so A1 means the first edge, the second A2 is the second edge, and so on. What can you bound it by? In terms of the probability of each one of them. You can think of it as a circuit, or you can think of it as n distinct edges. Give me the simplest bound, which you think not less than 1. See, compared to my usual square lattice percolation, here two adjacent edges are not independent in terms of the event is. They have an overlap. Clear, right? From the picture. The edge length was only S, but the rectangle which defined its status was much bigger than S.
Yes.
So the two neighboring ones are definitely going to impact each other. So I can't say that this is simply probability of A1 to the power n. That I can't say. But what can I say? How many of at least are independent? Even the simplest one. How many edges?
Which are not touching each other.
Yeah, how many? At least how many?
If I define a closed path, then half.
Doesn't matter closed or unclosed. N distinct. We are going to be slightly more liberal here. All I'm looking at n distinct edges. How many of them have no correlation with respect to each other? Can I say n by 4? A very safe bet. You could make it larger also if you like. But we'll see anything essentially order n is fine. In particular n by 4. Simply, that most. Any one particular. Okay, what about these? Now, these are more complicated. You'll have to use all sorts of properties of point-on-point process. What will it show in the point? Let's go to this. So we have weird thing, right? That at the center, the interference should be at most capital. Probability. Find this key to whatever it is. So don't be surprised by the integral. We also see something like this in our homework. Where sums over the Poisson process can be turned into integrals in fact exponential. Where this particular value is not important. What I'm going to tell you is that I can get an exponent which is exactly n. That is the most important. See, all of these are highly dependent on each other. This is not independent even across non-distinct edges. Pay close attention. When is B1 equal to 0? Now this center and this center, right? Essentially, B1 equal to 0 means that this is greater than n. B2 greater than 0 means this is greater than n, and so on. Now these points, even though they are far away, but could be highly correlated. There is nothing like what we just did, that n distinct edges in terms of A's, at least n by 4 have nothing to do with each other. Here, this interference is coming from the whole of R2. Take close attention, it's not clear, ask me right now. So this is the center and this is my center. I'm looking at the interference seen at this point, interference seen at this point. The interference is coming from all points in R2. And there is nothing like, if I go far away, that I can say something about their independence. However far I go, there is no sense of any interference being independent of each other. Not clear. Where is the interference coming from?
From all the points.
All the points. So suppose I'm looking at this point and a point far away, some other x. Can I claim that they're independent of each other? The interference seen at these points is independent of each other. That's all I'm saying. In the previous slide, we just did this for event AE. If you look at n distinct edges, at least n by 4 have nothing to do with each other in terms of these crossings.
Yes.
Because the number of points lying in distinct areas are independent. This particular event has infinite correlation. However far you go, there is no sense of independence. And that is why getting that to the power n is the most difficult task. This is still an exponent with respect to n. That's the surprising part. It could very well become just one event. P of B will equal to 0. In which case I will not get what I want. So this is the critical point. That I can still get an exponent with respect to n. Where the P2 is some number. The final exercise in this homework will do something which is an ingredient to this. By definition, I tilde of center 1. This is the center of the first edge. Is greater than equal to n. Really important. If all these events have to be true, it implies that the summation is greater than n times n. Individually, each of these events is greater than n, so this better be true. Now, since using Markov, what do I get? For any t, is true. First take the exponent and then so raising e to the power t on both sides and then applying Markovs. What's any t? Okay, this is the place at which eventually you have to encounter something like this. What is the expectation over? What is the randomness? Points from what?
From different realizations of the ground.
Yeah, this is the Poisson point process. The interference comes from the location. So that is with respect to the Poisson point process. Now, this is a very interesting quantity there. Computing expectations of the summation of something across the whole network. So this is where you will do something in your homework. So this is a very interesting result called Campbell's theorem. I was going to do the following. Summation of x plus is equal to integral over let's say doesn't matter really. If C is defined over R, then this integral to R. That becomes see the power of it. Not a trivial result at all. What is saying that you freeze a point and start counting f of x with respect to all points in the Poisson point process. Its expectation is nothing but the usual integral of f of x multiplied by so you show this for a small class of functions in here, which are simple functions. It is true for all functions. If you just you've seen this something is called standard machine. Have you seen standard machine? So the term is called the standard machine. So if you want to prove something like this for all functions there. You first prove it for step functions, which only take either value 0 or a constant. Once you're done with that, then you essentially use what is called as the monotone convergence theorem to apply it for all possible groups. In the homework, I've only asked you to prove it for simple functions. Okay, so this is the result. If you want a proof, you can look at any of the stochastic geometry books for the full proof. Right? Whatever I given the homework should be doing. So I'm going to apply that here. So essentially, what is this? This is summation over all points in the network area, which is being converted into an integral. That's the power of this. So this is same as here times exponentiation lambda t times d tilde x. This one here. Now this integral is over x. So think of this as the following geometrically. So x is some point. CI's are particular. So this is a nice picture. This is my square lattice. These centers, the points I'm drawing here are the centers of my edges. I'm looking at any point x here. These guys are the centers which I'm interested in. So how many are there at the level 1? There are at most 4 of them. How many are at the level 2? Level 12, and so on and so forth. So look at what is the sum over. The sum is over fixing an x with respect to these centers. So the first level you get 4, the second level you get 12. Subsequently, how many? 4 plus 8 times k for the kth level. And how much is the contribution in this from this nearest guys? How far is this distance? At most?
Square root 2.
Is it clear what is going on?
Yes,
Yeah. This is exactly as this is s prime. So this is s by square root 2. This is 2s by square root 2 and so on. So all I'm trying to bound with this function of d tilde x minus c I going on. That's all I'm trying to bound. You see either these centers of the edges. I just drawn in a particular way. Okay, take care of this. Unless I can show this bounded, there's nothing more to do. But this one is okay. This is at most how much? 4 plus 8k times. It will tell a particular function. What is that function? Simply, you don't even have to know. K S1. K goes around. Is this okay?
G tilde inside it, KS by root 2.
What is this s by root 2? Right?
Yes.
It's 2s by square root 2.
Okay.
That's the maximum distance. How many of them? These many of them. Okay. Now, where is this bounded? We go back and put a condition on G. That G should satisfy this to be bounded. If this is not bounded, I can't do it. So, in particular, you can say condition is very simple condition. The expectation of x with respect to G should be bounded. the technical term. So they reply that this sum is bounded. Okay, so there was that. Here, I've done that. So in particular, let's call this less than or equal to some. So here I have the choice of picking a t and pick t equal to 1 by k. This is true for every t by Marcos. Then pick t equal to 1 by k, which will make sure that this sum is at most 1. Right? T times this is at most k, that is 1 by k, so this is at most 1. So I'll apply the inequality. That it's x 1, that was 2 times x for x. So what again? Yeah. If I apply this here, eventually I will so this term is arbitrary. So T is essentially 1 by k. The N will show up. Yeah, so this is exactly what it is like. Some manipulations that way. The important point is this N is also here. So I can bring this inside and get a power. This is precisely what it is now. This is some algebra. What is the big picture? What have we done? We basically looked at these events that are highly correlated, written a very simple form. This is the event we want to control, but that is much smaller than this event. That then we just directly jump to the Marcos. At this point, apply Campbell's theorem. You actually bound this in terms of e to the power something n. This is already e to the power something n. Combining both, you will get e to the power. So the most important part was making sure that this exponent is the power of n. It's not obvious that that is true. That's what all the world is. Okay, so now how do I finish this whole thing? What I really want to look for that there is no closed circuit around. See, all I'm trying to do is to make sure that the square lattice percolates. And for that, a sufficient condition is that the probability with which there exists a closed circuit is going to 0. So now what have I bounded? I have bounded P of 1 equal to 0, again equal to 0 by something which is the inverse to the power n by 4 and P of P1 equal to 0. Pn equal to 0. What I really care about is the event. Did I define C or not? Here Cn was 1 or you just define Cn equal to n times both are by 3. This is the actual interesting quantity I'm interested in because it's open and closed. Depends on both of them being open and closed. Cn, the edge is closed if Cn is 0. So this is, you know how to form something like this when AIs and BIs are binary. So given that I have these two inequalities, can you give me a relationship for this? where Cn is nothing but n times Bn and everything is binary. Once you write this in P to the power, I can do it. You see, you use quasi short to get this. Critically use the fact that these are all binary numbers and then use quasi short. Okay, so now I have everything. Now tell me, how do I finish? I have two parameters of interest S, side length, and M. I want you to make sure I also computed the probability that there exists a closed circuit. This is exactly what it is. Is at most this much. Okay. Give me an answer that I can choose S and M in such a way that the probability of finding a closed circuit goes to this. So how many closed possible paths are there? Of length n around the origin. 4n times 3 to the power n minus 2. We did that last time. So this was our origin. We are interested in something like some closed circuit. So think of really this. Somewhere it has to cross. Last time also there was confusion that why doesn't I have to look here? I don't actually have to look at the y-axis. Suppose I just look at how many possible places that it can cross x. N by 3. And at each time I have three possible paths. I can go left, I can go right, except from where I am coming. So the total number of circuits of length n can be at most be 4 times n times 3 to the power n minus 2. The maximum circuits of length n around the origin can be 4. So the probability of finding a closed circuit at most 4n times this probability. The square would be, let's call it 2 to the power n. See, what we have done most importantly is that we are able to get the exponent. Everywhere that is very important. So let's define this to be. If I don't get this n by n, I can't do all this. In the original lattice, when we looked at the square lattice, this was just p to the power n. Because every edge was independent, open or closed independently. Now things are not open and closed independently. But we are somehow able to get that the probability that all of them are closed simultaneously is some probability to the power n, which is important. This can be large as long as this is less than 1, I don't care. But the exponent n is important. So all the hard work is to show that it's exponentially decreasing. And then as long as q is smaller than something, I get that this goes to by few more steps essentially. That there exists an n beyond which there exists nothing, because this is converging. So beyond an n, this whole thing is less than half. You don't know all this. It's called the Peel's P. You remember that argument? It is not 0. So it's 0, but this converges. Let's say less than some kappa. And then I know for large enough n, this whole thing is less than half. So I choose that n and make a box inside for which I am open, so I can always escape to infinity. That was the argument which we made for this normal square lattice percolation.
Write it in that place.
If you forget, I can't redo it. You have to remember things. This is not necessarily going to 0. All that we can say is this is converges. So if this converges, then there exists a large enough n for which the rest of the sum, the partial sum, is at most less than half. And then for small n smaller values, we make sure that the edge open probability is non-zero, so I can connect to somebody outside. So what we are essentially going to say that there is the probability that there is a closed circuit of large enough length is less than half. And inside, I can always make sure that I can connect to outside. That was the argument we made. Precisely the same argument holds as long as Q is smaller than something. What is that Q? When does this converge? That's all.
Q is less than.
What is that? When does this sum converge? You can get a lot of values. You can make sure that this is in fact less than equal to 1 for 11 minus square root 10 4 27. So all I have to do is to make sure that P1 plus P2, square root P1 plus square root P2 is less than this. And both those quantities are functions of S and M. P1, this guy is a function of S, and P2 is only a function of M. I want P1, square root P1 plus square root P2 to be smaller than something. So I will appropriately choose S and M. Once I do that, I'll pick an appropriate gamma to control my interference. Okay. That is how you complete this program. Okay, the basic idea is start with a supercritical Gilbert test model. Then define a square lattice where an edge is open when there are left-right crossings and top-bottom crossings of these rectangles, as well as the interference seen at the center is at most a large enough number m. Connect by the pure definition. What we really done is that if there is percolation in the square lattice, there is percolation in the SINR graph corresponding to the same geometry. We already know that the Gilbert's response is percolating. What we are ensuring by doing this left, right, and top bottom crossings is that the geometry is also maintained. That alongside my square lattice percolation, the Gilbert response also keeps percolating. And by using this, we also say that any edge which exists here also exists in SINR. Once you define this, all that remains is to fix or show that there exists large enough SNM for which the probability of finding a closed circuit in the square lattice is 1. So the most important part was to actually make this connection. Once you made the connection, then this machinery is already standard. That when does the square lattice percolate? The only non-trivial part is controlling, because they are highly correlated. There is no independence anywhere. So that's where the Campbell's theorem comes to your rescue. That these kind of expectations can be really complicated. This is an expectation of a sum of functions across all points in the Poisson point process. It looks intimidating, but the proof is rather simple that why it turns out to be just an integral over R2. Theorem statement is very simple. This expectation nothing but an integral over R2. That's how we accomplish this.